Hello, this is Travis Matthews, your instructor, and we're now going to go through special topics in Chapter 2 in your meteorology textbook. And Chapter 2 is about solar radiation and the seasons. So you can see this is what the front page looks like. That's a street view of downtown Chicago during a winter storm. Let's move on to the next page here. Page 31, I've got my highlights here. The one area I would like you to really pay attention to, other than just reading through the chapters, understand here in this paragraph says, for example, some people incorrectly believe that variations in the distance between Earth and the Sun cause the seasons, with summer occurring when Earth and the Sun are closest together, but Earth and the Sun are closest to each other on or about January 4th, in the midst of the northern hemisphere, which is us, our winter. Likewise, when the Sun is farthest from the Earth on July 4th, it's summer in the northern hemisphere. And the reason, they'll give you the reasons why later in the chapter, but the main reason why it's summer here on July 4th and the Sun is farthest away from the Earth is farther away from the Sun, is because we in the northern hemisphere are tilted towards the Sun, so we're getting more direct rays. Whereas in the winter, we're closer, but we are tilted away. In the southern hemisphere, which it's summer down there, is tilted towards the Sun. Okay, let's move on to page 32, another highlight here. I want you to know what energy is as a main specific. Also know what the joule is. Also know that power is the rate at which energy is released, transferred, or received, and that the unit of power is the watt. That's why when we buy light bulbs, we see 60 watt, 75 watt, 100 watt bulbs, and so on. Also here it says, in fact, while you are reading these words, an energy transfer is occurring as the chemical energy from the food you have eaten is converted into the kinetic energy, the energy of motion needed to move your eyes across this line of type. That was a very cool scenario that they're discussing there. Also here, understand what electromagnetic radiation is. It's also known as EMR for short. Also know what kinetic energy and potential energy are. And down here you have examples of these two forms of energy, of kinetic and potential energy, and make note of those as well. Let's move on to page 33. Page 33, I want you to know what conduction is. It's the movement of heat through a substance without appreciable movement of molecules. And then convection, the transfer of heat by the mixing of a fluid, is called convection. In terms, we've heard of conduction ovens and convection ovens. They follow similar principles. On to page 34, I'd like you to focus your attention on what radiation is. Of the three energy transfer mechanisms, we had conduction and convection. It says radiation is the only one that can be propagated without a transfer medium. That means it doesn't have to have anything to go through, some solid, liquid, or gas. Radiation can move through a vacuum, as it does through space when it's coming from the heat from the Sun, radiates to the Earth. Let's move on to page 35. At the top, you'll see where it talks about radiation, the characteristics of radiation. It says, radiation is emitted by all matter, thus everything will really specify that, including the stars, Earth, ourselves, and this book, is constantly emitting electromagnetic energy. So as you see the colors, that is the electromagnetic radiation coming at you. All right. Also down here in this highlighted area I have, it says, in the case of radiation, the waves are electrical and magnetic oscillations. That is, radiation consists of both an electrical and a magnetic wave. With the proper instruments, it says, we would detect these electrical and magnetic variations, hence the term electromagnetic radiation. So you want to have a good understanding of that. Moving on to page 35, we're talking about EMR. You need to know that all things emit. It says electromagnetic radiation, or energy, comes in an infinite number of wavelengths, but we can simplify things by categorizing wavelengths into just a few individual bands, as indicated in figure 2.7 and table 2.1. So you want to kind of take a look at figure 2.7 here, but really pay attention to these types of energy that are discussed in the figure down here in table 2-1. Moving on to page 37. Here we talk about, and I don't mean to highlight that bottom sentence there, it says, but of course the amount of radiation emitted and its wavelengths are not the result of mere chance. They obey some fundamental physical laws. Strictly speaking, these laws apply only to perfect emitters of radiation, so-called black bodies. And you need to know what a black body is. A black body is a purely hypothetical body. It's not perfect. It's not there. Hypothetical. It's not real. They do not exist in nature. What they do is they emit the maximum possible radiation at every wavelength, and you need to know that definition there for black bodies. Understanding the Stefan-Boltzmann law. Here, you need to know that the hotter bodies emit more energy than do cooler ones. That means, like if you're sitting out on hot concrete, it's emitting more energy than a cool concrete would. Let's move on to page 39. I'm going to skip page 38 here. I'll move on to 39. Page 39, you want to know about the did you know. And the did you know says to be comfortable, humans need to maintain a skin temperature of about 33 degrees Celsius or 91 degrees Fahrenheit. You want to read through that and understand that. Wien's law. You want to know that radiation emitted by the sun and earth or any other body is not of a single wavelength. Remember, we talked about there's all kinds of different wavelengths, hence the term. They're electrical and magnetic, so electromagnetic radiation. Nor are all wavelengths emitted in equal amounts. You're never going to have equal wavelengths coming out from a body. There's always going to be different ones, wavelengths coming across. All right, Wien's law at the very top of page 39 says, Wien's law tells us that hotter objects radiate energy at shorter wavelengths than do cooler bodies. This kind of goes along with what we were discussing on the previous page a couple minutes ago. You also want to know that shortwave radiation is considered to be wavelengths less than 4 microns. That backwards cursive U thing and an M is called microns, or micrometers. Radiation emanating from the Earth's surface and atmosphere consists mainly of that having wavelengths longer than 4 microns. So long wave is larger than 4 microns, and shorter than 4 microns right there is considered shortwave radiation. Know those definitions of that. Let's move on to page 43. Page 43, now we're getting into the seasons and the causes for the Earth's seasons. You want to read through this area called the Earth's revolution and rotation. There's a lot here I have highlighted, but you want to note specifically what the ecliptic plane is, the revolution. You also want to know what perihelion is, aphelion, and also what rotation is. The star Polaris, about the North Star, what its importance is as well. But my suggestion is read the whole section, but you're focusing really a lot on these definitional terms. Over on page 44, a very good description of picture of the seasons and Earth and how it's tilted towards the sun and so forth. So you want to read through that and have a good understanding. Figure 213 is just a hypothetical situation if all things were equal. Up here it's when we're closer and further apart, as discussed at the very beginning of this lecture. On page 45, under the solstices and equinoxes, says right here on the left column in yellow, says during 6 months of the year, the northern hemisphere receives more sunlight than does the southern hemisphere. During the other 6 months, the southern hemisphere receives a greater amount of insolation, radiation. You can see that it's how the Earth's tilted over here. But you want to know the June solstice and the dates, the December solstice, the March equinox, and the September equinox. And I always remember the equinox very well as a young child growing up in grade school. I remember our second grade teacher would always take eggs and stand them on end. And if you've never done that, on the equinox, March or the September, you can stand an egg on end. Also, you might have heard people say they could take certain types of brooms and stand them straight up. Eggs are easier because they're not going to fall and break. But it's something that you might want to try here come this March 21st or so. Okay, moving on to page 46, the period of daylight. I've got highlighted here. It says on the June solstice, any place north of the Arctic Circle has 24 hours of daylight. That's on the June solstice. You want to know that. Just a short distance south of the Arctic Circle, there is almost, but not quite, 24 hours of daylight. That's the, as you're close to it. It says moving toward the equator, the period of daylight decreases until reaching the equator. It says moving into the southern hemisphere, day length shrinks until when you get to the Antarctic Circle, which is 66.5 degrees south. That means there is 24 hours of darkness or night. It says the opposite pattern, of course, holds for the December solstice. That means the northern hemisphere north of the Arctic Circle will be dark 24 hours a day, and the Antarctic Circle will have 24 hours of sunlight. Also, you need to understand about the solar angle. And the solar angle is the angle of the sun coming at us. It's not when is it directly overhead or is it at an angle. And they do a description here, but you want to know the definition of beam spreading. There's also a picture right here on figure 2-17 on page 47 that talks about, shows a light, a flashlight, direct sunlight coming in. It's direct, and then shows you as it comes at an angle. When it comes in at an angle, like in figure B here, it's being spread out over a larger space. If you can see, that circle is actually larger at that angle than it is when it's directly over. So that means that the beam spreading and the energy is not as intense, so it's going to be cooler. So that's why we, kind of goes to the seasons here on Earth and in the northern hemisphere where we're located. Okay, moving on to page 50. We're almost done here. I want you to understand these highlights. It talks about, gives you highlights of the June solstice, the December solstice, and the equinoxes. So you want to kind of have a good idea of what those are. And then over on the last page, page 51, I really want you to make note. There's a lot of questions here, but make note and be able to answer questions 5, questions 10, and questions 12. Question 5 says place the following wavelength bands in correct order of wavelength, and you have to put them in order. And it says question 10, what is the most important factor responsible for seasons on Earth? Question 12, what is the significance of the Arctic and Antarctic circles? We just discussed them about the daylight and the night, 24 hours a day. And it also has some other factors as well. Well, that is chapter 2 in a nutshell on this video lecture. Just make sure you make note of all the highlighted areas. My suggestion is to read through the chapter as well. That way things get more concrete in your brain, and then you're better able to take the quiz, work on the exam as well. If you have any questions, feel free to email me, and good luck.